Alright, so this is section 5.5, or multiple angle formulas. It's not too bad. This whole section is full of formulas, though. I don't have my students write it down. You guys don't have to write it down, but you do need to be aware of the page numbers if you're using the book, which is on page 405, the first double angle formulas. For this set of problems, it gives us a triangle. It's a right triangle, 4 and 1, with this angle being theta. It doesn't give us this, but square root of 17, diagonal theorem is easy to figure out. First one wants us to find cosine 2 theta. Now, cosine 2 theta is very interesting, and there's 3 different ways we can write this one. And it doesn't really matter, but I'm just going to use, it matters in terms of what we need to get the problem solved in. For this particular problem, it doesn't matter though, so I'm going to use this one. Cosine squared theta minus sine squared theta. Okay, basic. I like that one for this type of problem. So plug in what we have. Cosine of theta is adjacent over hypotenuse, so it's going to be 4 square root of 17 squared minus opposite. Over sine is opposite of our hypotenuse, so 1 square root of 17 squared. Shoot the squares to top and bottom, so we get 16 over 17 minus 1 over 17. Add them together, or subtract them together, I guess in this case, and we get 15 over 17. See, pretty basic indeed. Moving on, 15 is cosecant theta. Cosecant theta, there is no formula. We need to use our trig identities in order to rewrite it. Cosecant theta is the same as 1 over sine theta. So, let's use the formula for sine theta. This should be 2 theta, my bad. So that's the same as 2 theta. Alright, so sine 2 theta. That one has one formula, so we got 1, 2 sine theta cosine theta. Alright. So again, plug in our numbers for sine theta and cosine theta, which we get, and I'm just going to do the bottom. Let's just remember it's all being divided, or underneath 1. So that means we get 2 opposite over adjacent, 1 over square root of 17. And then we're going to get 4 square root of 17, which we multiply that out, which is 4 over square root of 17. We just multiply straight across. This 2 we get multiplied by the 4, so technically we're going to get 1 over 1, 8 over 17. It's a complex fraction, we just flip it. It's just 1 over 1, so this easily turns into 17 over 8. And that's the answer for cosecant 2 theta. So whenever you have cosecant, secant, or cotangent, you just flip it 1 over that number and solve it for that way. Now, moving on to sine 4 theta. Of course, we don't have a formula for 4 theta, but we can use some tricky substitution. I'm going to before I let that happen, I'm going to rewrite sine 4 theta as sine 2 theta. Okay? I can do that simple multiplication. So now let's let u equal to theta. Okay? Again, we've done u substitution before, if you have, and we just let this happen. So we get sine 2u, which if we expand that out is same thing right here. So it's going to be 2 sine u cosine u. All right. Plug in our u back in, so we get 2 sine 2 theta cosine 2 theta. Now, normally we're going to expand all that out. So that means we normally would expand all that out. So we would technically get 2 times 2 sine theta times cosine theta all times, and we'll just do this one again, cosine squared theta minus sine squared theta. That's if we expand it all out. Of course, we don't have to, because if we think about it, we already know what this value is going to equal. That's going to equal 15 over 17. We kind of already know what this value is going to equal based off this previous problem right here. It's going to equal 8 over 17. So therefore, we get 2, 8, 17, and then 15, 17. Multiply all that out, and we should get 240 over 289. Hopefully, this type problem is simple, straightforward, you just go from there. This type problem is a little tricky, you have to use your trig identities to rewrite it. This type problem is probably the most complicated one because that 4 theta, we have to use substitution to substitute that out. That's how you do the basic problems if you're given a triangle. Now, moving on, we have some other sets of problems that can be tricky, still using those double angle formulas. So I'm going to erase all this. One of the big things with these formulas is being able to recognize what you have and when to go write them differently and not write them differently, or when to go backwards. And that's a big deal. So I'm going to do 2 examples of what I mean by going backwards and stuff. So this is one of the first examples. It says find all the solutions, which again, just solve it, all right? This one we need to expand out though. We cannot combine those because this is a 2x and that's an x. So therefore, write this one out, which based off our formula we have and how to expand that is this. From here, what do they have in common? Big common theme so far, so they have sine x in common, and we get that. Set each one equal to 0. And solve it. This one's easy, we can easily do that one in our heads. We get cosine x equals 1/2. So, when on the unit circle, is that true? Between the interval from 0 to 2 pi. Sine is your y-coordinate. It equals 0. So our answers for this one, 0 and pi. Our answers for 1 cosine equals 1/2. Pi over 3 and 5 pi over 3. And those are our answers for that type of problem. Okay, so that one's pretty straightforward. This one's not so straightforward, so we have that 4. And we already have a sine x, cosine x, equals 1. The 2 is kind of a difficult. The 4 is a problem because 4 is not in our multiple or double angle formulas. But, like we did previously on another problem, I can split this 4 up to read like this. Okay? Those are the same thing. 2 sine x cosine x, that looks very similar to from how I went from here to here. So, let's go, that's just You have to realize what they're similar and then be able to go backwards one way or the other. Expanding the formula and then condensing the formula at the same time. Solve for this. Equals that. Now this one's tricky because we have that 2x is kind of an issue. But it's not too bad because all you really have to do is say, well, when does sine, what I tell my students, when does sine equal 1/2? That answer is at pi over 6 and 5 pi over 6. Set those equal to 2x. Now, here's our issue. If it's in between our answers are between the interval of 0 to 2 pi. What we have to do is also go ahead and add a 2 pi n to both of those. So you rewrite it out. So we add that to both of those. All right, solve it out, which divide by 2. So when we divide by 2, we get, this becomes x pi over 12 plus pi n x 5 pi over 12 plus pi n. Now, my students have a hard time with this, and I try to explain the easiest way, but the n, when n equals 0, evaluate these until our values of those are greater than 2 pi. Because remember, our intervals from 0 to 2 pi. So when n equals 0, that means our only answers are pi over 12 and then 5 pi over 12. Okay? Actually, I'll just come up here. So we take these two equations. When n equals 0, that is, we plug 0 in, our only two solutions are pi over 12 and 5 pi over 12. Now when n equals 1, okay, plug n equals 1 in, so we get pi over 12 plus pi, which is just 13 pi over 12. Still less than 2 pi. Add n equals 1 there, so we get 5 pi over 12, which is just 17 pi over 12. Still less than 2 pi. When n equals 2, this turns into 2 pi, that turns into 2 pi. Automatically, it's bigger than 2 pi. So here's our answers right there. Okay, it's kind of a complicated one. This is one we have to go take our equation, recognize that we can separate it out, solve for it, take this, and realize when sine equals 1/2, which pi over 6 and 5 pi over 6. But because we have this 2x, because we have a number associated with this x, we need to add those 2 pi in and solve for it, and then do how many innovations or how many times n can happen, so it'll be less than 2 pi. So that's basically how to use your multiple angle formulas. The next type of formulas I'm going to show you is the power reducing formulas. And those ones can be very time consuming. The power reducing formulas are mostly used for your going on to calculus. It relates mostly to that field. So I'm just going to do one example. Again, if you're in my class and following on the book, it's on page 407. There's 3 formulas there. We'll just do a quick example. Now the power reducing formulas you're using to get rid of all the powers. That means we do not want any powers in our answers. So we're actually going to expand it quite deeply. Cosine 4x is not on our power reducing formula, but cosine squared is, so we write this as cosine squared x times cosine squared x. Now, cosine squared x, that equals 1 plus cosine 2u all over 2. Sorry, 2x, my bad. You see we have two of them being multiplied together, so multiply this one by itself together. Multiply straight across. So the top we have to FOIL it, so we get 1 plus cosine 2x plus another cosine 2x. Now, this is cosine 2x times cosine 2x. Does not turn into cosine 4x, but rather turns into cosine squared 2x. And it's all being divided by 4. Okay, we can rewrite this now as 1 plus 2, because I have 2 of those. 2x plus cosine squared 2x, all being divided by 4. Okay, we're not done now because we actually created another power. First, before I do this, I'm going to go ahead and pull out that 1/4. So we get that. We need to reduce down this cosine squared x. That's just this, so substitute it in. So that means if I come up here, now, sorry, this should be 2x, my bad. What I do, let u equal 2x. So that means I'm just evaluating cosine squared. That means this turns into cosine squared u. It's a little bit easier for us to just see mathematically. So that means this turns into 2u over 2. Okay? So I'm going to solve this out real quick, and I'm going to skip a step. But the deal is I want to pull this 2 out. So what I'm going to end up doing, actually I won't skip this step, I'll show exactly what I'm doing. I distribute the 2 over, so everything's now divided by 2, and I made sure I multiply. Everything is top and bottom multiplied by 2. That's where the 1 I get 2 over 2. It's still 1. So now I pull out a 2. And when I pull out this 2 from all this, multiply by this 4, so I get 1/8. This will be 2 plus 1, so 3. 4 cosine 2x plus cosine 2u. Our last step. Remember, we let u equal 2x. Let's plug 2x back in. So that means we get 1/8 cosine 2x. If I plug 2x back into u, that's going to turn into cosine 4x. Okay? And that problem cannot be reduced any further. That's as far as you go with that problem. These problems are actually, they're not difficult in terms of what you're doing. It's only difficult in it's not difficult in terms of what you plug in. It's difficult in terms of how long it takes to reduce it down. Because once you start reducing one down, the possibility of getting a double increases. Or you just gotta keep reducing until you get more powers. It's time consuming, mostly. That's why they're difficult, and that's why a lot of people don't like them. But it's just time consuming. In terms of math, it should be straightforward math. Yes, there's some complexity. It's kind of complicated right here. But if you've been doing fractions enough, it should make sense. Okay, so those power reducing formulas, there's really not many of those. So the next examples I want to show. We have these half angle formulas. So we have half angle formulas, which if you follow in the book that we have at least, which, or you can just find them online, is it's on page 408. But half angle formulas, and we'll start out with for the set problems. It gives us a picture. We have that, and then 8, 15, that's right. And so we have to find the other side, which is do Pythagorean theorem again. And we get 17. Okay, so the first example I'm going to do is cosine theta over 2. Now, half angle formulas, in our book it has cosine u over 2 equals plus or minus the square root, and I'll actually just write it out there so you guys can see it. Why does it do plus or minus? Oh, the signs depend on which quadrant we lie in, and in this one, because there's no, we don't have positive values for this quadrant, for this triangle, we're going to get a positive value. But this equals plus or minus, I'll just write it all out, I'll explain that again. 1 plus cosine 2 theta all divided by 2. Alright, again, it's plus or minus, but because these are all, because this quadrant lies in, or at least that triangle, it depends on what quadrant u over 2 lies in, we have only positive values, so that's going to be quadrant 1. Therefore, we only have a positive answer. So cosine sorry, there's no 2 right here. My bad. Theta over 2. My bad about that, it's just cosine theta. So, plug in what we have. Cosine theta is 15 over 17. So, 1. It's all square root. We get that. We need to rewrite the inside because it's a complex fraction. So, we change this 1 to 17 over 17 plus 15 over 17. All divided by 2, and if I want, I can imagine that's being divided by 1. So this further step goes, sorry, my straight math is not so great. Equals 32 over 17, all divided by 2 divided by 1. So this turns into 32 divided by 34, which they have a 2 in common. So it's 16 over 17. Now remember, that's all underneath the square root. So you take the square root of that. Make sure the square root goes to both top and bottom. So we get 4 square root of 17. Don't like the square root of 17 on the bottom. Multiply square root of 17 top and bottom, so we get 4. Like that. Again, when it has a picture, it's a little bit simpler. So let's do another example of a half angle formula. So for this problem, it just says 75 degrees, and it says use the half angle formula to determine the exact values of the sine, cosine, and tangent of the angle. So if we do that, we have sine 75. What that means is sine of 150 over 2. Right? Because I already cut it in half. So double it up. So therefore we get 150 is my u, and the sine one, because 75 lies in quadrant 1, we're going to get a positive answer. This one becomes the square root 1 minus cosine 150 divided by 2. Okay, it's because my u is 150 cosine of u, so 150. And then 150 is on our unit circle. How convenient of the book to do that for us. So we get the square root of 1 minus, and it's the negative square root of 3 over 2 divided by 2. So again, rewrite the inside stuff, which we get so which therefore we get 2 over 2. So we get 2 plus the square root of 3 over 2, all divided by 2 over 1. And it's all the square root. So after we get that, we get 2 plus the square root of 3 divided by 4. We take the square root goes to both top and bottom. So it really only goes to the bottom, so we get 1/2 2 plus square root of 3. And that's the sine one, so we do the same thing with the cosine. Now, if you look, they're the same thing. The only difference between the sine and the cosine is the negative value, right here. This and this. This one ended up being positive, this one's going to be negative, so I'm going to take a hunch. And if I did the same math, because the negatives, that's all it changed was the negatives, I'm going to end up with 1/2 square root of 2 minus square root of 3. Okay. Last one is tangent. Tangent, there's 2 ways to write it. What this tangent one is, I'm just going to use one of them, doesn't really matter. I'm going to use 1 minus cosine of u, which our u is 150, so cosine 150, all over sine of u, which is 150. Okay, plug in our values for cosine and sine evaluated at 150, and we get 1 minus the square root of 3, 1 minus negative square root of 3 over 2, all divided by 1/2. Okay, so let's go ahead and simplify the top part, and simplify the top part, so we get 2 plus square root of 3 all over 2 divided by 1/2. It's a complex fraction again, so we get 2 times 2 plus square root of 3 all over 2. The 2's can cancel on the outside, and we get that. We just solve it. which for the most part, you guys should be able to do. Of course, the answer for what they do, it's a different thing, but we got the same answer. So either way you want to work it, you get the same answer, whether you do the other formula or not. And that's half angle formulas, and I'm looking at the other examples that I do that my students have to do, and I think that's it. There's also product to sum formulas. I'm not, for my classes, my students, I don't give them those type of problems because it's just the same stuff. Plug and chug in a formula. So, that's it.